Look up at the sky right now. Chances are, you'll see clouds. They're so common, so ordinary, that most of us stopped really looking at them sometime around childhood. We see them every day, but we don't really see them anymore. But here's the thing. Clouds are anything but ordinary. They're floating rivers carrying more water than all of Earth's actual rivers combined. They're sculptors of climate, shapers of weather, and painters of the sky. Some clouds can weigh as much as a jumbo jet, yet they float. Others move faster than a Formula One race car, and a few are so rare that most people will never see them in their entire lives. Today, we're looking up. We're going to explore the science, history, and surprising secrets of clouds, from the ones you see every day to the ones that shouldn't even exist. So settle in, and let's start with the most basic question. What exactly is a cloud? A cloud looks light and fluffy, like cotton candy floating in the sky. And in a way, it is light. The water droplets are so small and so spread out that they can stay suspended in air. But here's what's surprising. The average cumulus cloud, one of those puffy white clouds you see on a nice day, weighs about 1 million pounds. That's roughly 500,000 kilograms, about the same as a fully loaded jumbo jet. Wait, how can something that weighs as much as an airplane just float in the sky? The answer is density and distribution. A cloud that size contains about 500,000 kilograms of water, but that water is spread across a volume of about 1 cubic kilometer. That's 1 billion cubic meters. So while the total weight is massive, it's so spread out that the density is actually less than the surrounding air. Each individual water droplet is incredibly tiny, about 20 micrometers in diameter, which is smaller than the width of a human hair. These droplets are so small that they fall extremely slowly. At that size, a water droplet falls at about 1 centimeter per second. Meanwhile, the air around it is constantly moving upward due to thermal currents, updrafts created by the sun warming the ground. So the droplets aren't really floating, they're falling. But the air beneath them is rising faster than they're falling. It's like walking down an escalator that's going up faster than you're walking down. But here's where it gets interesting. These droplets are actually falling around something. They need a surface to form on. You can't have a cloud without dust. Every single water droplet in a cloud formed around a microscopic particle dust. Pollen, sea salt, even pollution. These particles, known as cloud condensation nuclei, are absolutely essential for cloud formation. Without them, water vapor in the atmosphere would need to be much more saturated before it could condense into droplets. In perfectly clean air, with no particles at all, you could theoretically have humidity levels of several 100% without any clouds forming. The dust in our atmosphere is actually what makes clouds possible. For most of human history, clouds didn't have names. People looked up and saw, well, clouds. White things in the sky, maybe they'd described them. Dark clouds, rain clouds, wispy clouds. But there was no system, no way to communicate precisely about what you were seeing. That changed in 1802, when a British pharmacist named Luke Howard gave a presentation to a scientific society in London. He proposed a classification system for clouds based on Latin names, similar to how we classify plants and animals. He identified 3 basic types: cirrus, meaning curl of hair, cumulus, meaning heap or pile, and stratus, meaning layer. Everything else was a combination or variation of these 3. This might not sound revolutionary, but it was. For the first time, a sailor in England and a farmer in France could look at the same type of cloud and call it by the same name. Scientists could compare observations. Weather prediction became possible in a way it never had been before. And here's something fascinating. The poet Johann Wolfgang von Goethe, one of Germany's most famous writers, was so impressed by Howard's cloud classification that he wrote 4 poems about it. Clouds had captured the romantic imagination. They weren't just weather phenomena anymore. They were part of how we understood and appreciated the natural world. Howard's system, with modifications, is still what we use today. When a meteorologist talks about cumulonimbus clouds, they're using a naming system that's over 200 years old. Before modern weather forecasting, sailors and farmers became experts at reading clouds. There's an old maritime saying, mackerel sky, never long wet, never long dry. Mackerel sky refers to altocumulus clouds that look like fish scales. They often indicate that weather is about to change, though not necessarily to rain. These folk predictions weren't always accurate, but they were based on generations of observation. People learned to read the sky like a book, because their lives and livelihoods depended on it. Now, let's talk about clouds that break the rules. Clouds that form in places or ways that seem impossible. And one of the strangest is the morning glory cloud. Morning glory clouds appear primarily in one place on Earth, the Gulf of Carpentaria in northern Australia. They're roll clouds long, horizontal cylinders that can stretch for hundreds of kilometers and move at speeds up to 60 kilometers per hour. They look like massive tubes rolling through the sky, and they appear almost exclusively in the early morning during September and October. What makes them so rare? They require a very specific set of conditions. Sea breezes from opposite directions that collide, creating a rotating wave in the atmosphere. The moisture condenses on the upward-moving side of this wave, creating the visible cloud, and evaporates on the downward side. It's like a wave in the ocean, except it's a wave made of air, and the cloud is the foam on top of that wave. Glider pilots travel from around the world to ride these clouds, surfing the updraft along their leading edge. It's one of the most spectacular sights in aviation. But morning glory clouds aren't the only rare ones. There are also noctilucent clouds, which form at the very edge of space, about 80 kilometers above Earth. That's 5 times higher than commercial airplanes fly. At that altitude, the air is incredibly thin, about 100,000 times thinner than at sea level. These clouds are so high that they still lit by the sun even after it has set below the horizon, which is why they're called night-shining clouds. They glow with an eerie, electric blue light against the darkening sky. They're made of ice crystals, but the ice forms around meteor distactual particles from space that burn up in Earth's atmosphere. Here's the really interesting part. Noctilucent clouds are becoming more common. Before the late 1800s, there are almost no historical records of them. Now they're seen regularly during summer months at high latitudes. Scientists think this might be because of increasing methane in the atmosphere, which breaks down into water vapor at high altitudes, providing more moisture for these clouds to form. They might be a visible sign of climate change, appearing at the very edge of our atmosphere. Speaking of clouds at extreme altitudes, the highest clouds in our solar system aren't on Earth. They're on Neptune, where methane ice clouds form at such high altitudes and move so fast that winds can reach 2,000 kilometers per hour. That's faster than the speed of sound. Neptune's clouds are some of the most dynamic weather features in the entire solar system, and we're still learning how they form. Here's a question that sounds simple but isn't. Do clouds make Earth warmer or cooler? The answer is both, and it depends on the type of cloud, the time of day, and where it is. Low, thick clouds, like stratus clouds, act like a blanket during the day. They reflect sunlight back into space before it can warm the Earth's surface. This cooling effect is massive. Without clouds, Earth would be significantly hotter. Studies suggest that clouds reflect about 20% of incoming solar radiation. That's enough to keep global temperatures several degrees cooler than they would otherwise be. But at night, clouds do the opposite. They trap heat that's radiating from Earth's surface, acting like a blanket that keeps warmth from escaping into space. This is why cloudy nights are usually warmer than clear nights. The clouds catch the infrared radiation and send some of it back down to Earth. High, thin clouds, like cirrus clouds, mostly trap heat rather than reflect sunlight, so they have a net warming effect. Low, thick clouds mostly reflect sunlight, so they have a net cooling effect. Overall, clouds have a slight cooling effect on Earth's climate, but it's a delicate balance. This makes clouds one of the biggest uncertainties in climate science. As the planet warms, will we get more clouds or fewer? Will they be higher or lower? Thicker or thinner? Different types of clouds respond differently to changing temperatures, and small changes in cloud cover could either amplify or reduce global warming. It's one of the reasons climate models still have significant uncertainty. We're still figuring out exactly how clouds will respond to a changing climate. Clouds also play a crucial role in the water cycle, obviously. But here's what's less obvious. A single water droplet might cycle through the atmosphere as many as 6 times before it finally falls as rain and makes it to the ocean. It evaporates, forms a cloud, falls as rain on land, evaporates again, forms another cloud, and so on. The average water molecule spends about 9 days in the atmosphere as part of a cloud before completing its journey. That 9-day journey might take it across continents, high into the mountains, or out over the ocean. Here's something fun. You can create a cloud in a bottle using just a few household items. All you need is a plastic bottle, some warm water, and a match. Pour a little warm water into the bottle and shake it to create water vapor. Light a match, blow it out, and quickly drop it into the bottle, then cap the bottle immediately. Now squeeze the bottle hard. Then release it. When you release it, a cloud will form inside the bottle. What's happening? The match provides smoke particles, those cloud condensation nuclei we talked about earlier. The squeezing increases the pressure and temperature inside the bottle. When you release, the pressure drops rapidly, which causes the temperature to drop. The water vapor, now cooler, condenses around the smoke particles, forming a visible cloud. It's the same principle that creates clouds in the atmosphere. Air rises, expands, cools, and the water vapor condenses into droplets. You've just recreated a natural phenomenon in a plastic bottle. But humans don't just make clouds in bottles. We make them in the sky too. Contrails, those white lines behind airplanes, are artificial clouds. They form when hot, humid exhaust from jet engines meets the cold, low-pressure air at high altitudes. The water vapor in the exhaust condenses and freezes almost instantly, creating ice crystals that we see as white lines. Some contrails disappear quickly. Others spread out and can last for hours, eventually covering large areas of sky. These persistent contrails can actually affect local climate by trapping heat, similar to natural cirrus clouds. Some estimates suggest that contrails contribute as much to global warming as all the CO2 emitted by aviation combined. And speaking of human-made clouds, cloud seeding, the practice of adding particles to clouds to encourage rain, has been used since the 1940s. China used it extensively during the 2008 Beijing Olympics to prevent rain from disrupting the opening ceremony. They seeded clouds before they reached Beijing, causing them to release their rain early. It's still debated how effective cloud seeding really is, but it is now used in over 50 countries for everything from increasing rainfall to reducing hail damage to crops. Finally, here's something that connects everything we've talked about. Clouds are one of the most photographed subjects in the world, yet no two clouds are ever exactly the same. Every cloud you see is unique, shaped by temperature, humidity, wind patterns, the particles it formed around, and countless other factors. The clouds you saw this morning will never exist again in exactly that form. They're temporary sculptures, always forming, changing, then fading, which makes every sunset, every storm cloud, every wispy cirrus formation a once-in-universe event. So the next time you look up at the sky, remember, those aren't just clouds. They're floating oceans heavier than jets. They're classified by a 200-year-old system created by a pharmacist poet. Some of them glow at the edge of space. They control our planet's temperature in ways we're still figuring out. And every single one is completely unique. Clouds are one of those things that are everywhere, yet still full of mysteries. And that's what makes them worth looking at. If you enjoyed this, hit that subscribe button. Next up, we're diving into something even bigger, facts beyond what you see every day. Thanks for watching, and keep looking up.